Let's talk about generators. This is how we light up the city. We let water spill over the edge of a dam. It falls a far distance, gaining a lot of kinetic energy, and then we use that kinetic energy to turn turbines at the bottom. Those turbines are used to turn coils in a magnetic field. Now, anytime I turn copper coils in a magnetic field, I'm changing the number of field lines that pass through the loop. Think of this loop as a butterfly net. And think of these magnetic field lines as butterflies. I'm catching butterflies, right? Now what am I doing? I'm just making a map. Okay, I'm just hitting butterflies. They're not going through the net. Okay, so to catch them, I got to go this way. If I turn this loop in that magnetic field, I'm catching butterflies, I'm not. I'm catching butterflies, I'm not. I'm catching butterflies, I'm not. I'm constantly changing the number of field lines that pass through this loop. Now we learned that that induced current is energy. It has to come at a cost. That means if I'm the one turning the loop, have to do positive Varric. Well, that tells me immediately which direction the current is going to be traveling in that loop. If I turn it that way, the current's going to be traveling that way. How do I know? Because that current would give me a dipole, a little magnetic north and south, that is lined up with the external field. Now, what I'm trying to do is I'm trying to turn that loop. And if that dipole is lined up with the magnetic field, turning the loop is going to force the dipole the way it doesn't want to go. Think of that dipole as a compass needle. It wants to stay there. And I'm forcing it against the field. As soon as I get it anti-aligned, if it stayed like it is now, it would be helping me turn. But no, it changes direction so that I'm always fighting that dipole. And the bigger the current, the bigger the fight. Pat, you're having a hard time staying awake, you're yawning there. Come on, I've got something for you. We're going to use Pat's Mondo muscles to light up our city. Come over here, Pat, and turn this crank. He is the hydroelectric dam, and he is turning the crank. Right now, nobody's got their lights on. It's middle of the night. It's really quite easy to turn, isn't it?
Yeah.
All he's doing is fighting friction. I turn on a light. Oh, that made it harder. Okay. Now there's current in that loop in the magnetic field, and he has to fight that dipole. Now, if I turn on another light in parallel, I double the current. And if I triple the current, now, keep turning it. There's one more switch I can turn, and this will short out the system, make the resistance go to negligible, and 1, 2, 3, and that's what happens if everyone in Los Angeles turns on their air conditioner at the same time. You're done. Let's give what I have. If all of those air conditioners are connected in parallel, when they're all turned on at once, that essentially lowers the resistance of Los Angeles down to 0. And suddenly we're asking for a huge amount of current, meaning all of that current has to go through the coils that are being turned by the turbines. Well, if I have so much current and so much of this fight that the falling water can't turn the turbines fast enough, then I get a brownout and no one gets their air conditioner.